Hello class, welcome to Geology 234, Introduction to Remote Sensing. I'm Noelle Frempter, your instructor this semester, and let's get started with our first lecture. Okay, let's start with the agenda. So we will be going over what remote sensing is, why we use remote sensing, the limitations of it, and then a part 2 of this lecture, which will be given next week, will go over the electromagnetic energy interaction in atmosphere, and the energy interaction with Earth's surface, and then vegetation mapping. So remote sensing is an art and a science of obtaining information about an object or feature without physically coming in contact with that object or feature. And that was a quote from Lilason and Kiefer from 1987. And a similar quote, RS, the acronym, is an art, science, and technology of obtaining reliable information about physical objects and the environment through different techniques recording, measuring, and interpreting imagery and digital representation of energy patterns derived from non-contact sensor systems. And that was Colwell in 1997. So you can collect data without coming in contact with the object. For example, taking the temperature of someone with a thermometer, like in this photo on the left. This cute baby is getting its temperature taken from a thermometer, which is an example of remote sensing, but it's not an example of geospatial application. So all these measurements that are taken have some sort of connection to space or place within them. Here is a much more strict or specific definition of remote sensing, and it's a mouthful. The non-contact recording of information from the ultraviolet, visible, infrared, and microwave regions of the electromagnetic spectrum by means of instruments such as cameras, scanners, lasers, linear arrays, and or area arrays located on platforms such as aircraft or spacecraft, and the analysis of acquired information by means of visual and digital imaging processing. Whew, that is a mouthful. But this is what we mean when we talk about remote sensing in the geospatial world. That previous definition used the words platform and sensors, which are key attributes of remote sensing. Here's an example of a Google car driving around with a Google camera taking pictures. And so the camera in this case is the sensor. So it takes pictures of different parts of the visible electromagnetic spectrum, which we will talk about later. And then the platform in this example is the thing upon which the sensor is mounted. So it's the Subaru, the car. The platform in this example is the Google car. A true example of remote sensing is Landsat 8 satellite. There have been a number of different Landsat satellites, and each one of them takes different photos of the Earth. There are two different sensors on board that are able to collect data. One is the operational land imager, which is similar to a big advanced camera, and we will talk more about that later. And there is also a thermal infrared sensor, which is kind of distinct and takes images on different parts of the electromagnetic spectrum. And more details on that will be given in the next couple weeks. Remote sensing requires two elements, a sensor and a platform, which I have already discussed in previous slides, but now I'll get more detailed. A satellite platform is placed in Earth's orbit. The sensor can collect information across large geographic areas and circle back to the same areas on a consistent cadence. Aircraft and aerial platforms are more targeted than satellites, typically collecting imagery over a smaller geographic area or field of view. The way that aerial imagery is collected varies depending on the aircraft type and the sensor type, active or passive, which we will talk about later as well. There's different types of aerial aircraft. So we have high, mid, low altitude. The high altitude aircrafts carry the sensor collecting imagery 30,000 to 90,000 feet from the Earth's surface. This is a favorable platform for intelligence and can sometimes be piloted remotely. General aviation aircraft will carry a sensor 100 to 10,000 feet above Earth's surface. During flight, the sensor will capture consecutive overlapping images with a smaller field of view. These images are processed into imagery data sets, And then because they fly at a lower altitude and slower speed, general aviation aircraft often provide higher quality imagery than high altitude aircraft and are therefore a more popular aerial platform choice. General aviation aircraft provide imagery for numerous applications, including crop monitoring, changing land use, and land cover. More remote sensing platforms include pigeons starting in the mid 1800s, which carried mounted cameras and took some of the first aerial shots. And then other platforms include ground-based platforms and then satellites. So there's three main platforms: ground-based, airborne, which are airplanes and aircrafts, and then satellites. Satellites are the most stable platform aloft, which is spaceborne. The first remote sensing satellite was launched in 1960 for meteorology purposes. Now, over 100 remote sensing satellites have been launched, and more are being launched every year. Satellites can be classified by their orbital geometry and timing. So, three orbits commonly used for remote sensing are geostationary, equatorial, and sun synchronous or polar, which I will discuss later in this lecture. Remote sensing platform airborne are aircraft-based aerial photographies, and it kind of invented the discipline of photogrammetry. Low altitude aircrafts typically fly below altitudes where supplemental oxygen or pressurization are needed. So that's 12,500 feet above sea level. They are good for acquiring high spatial resolution data limited to a relatively small area. Mid-altitude aircraft have an altitude limit under 30,000 feet above sea level. This includes a number of turboprop aircrafts. Often at higher altitudes, there is less turbulence, so stability is better. This class of airplane is used when stability is more important and when it is necessary or desired to acquire imagery from a greater distance than available from low-altitude aircrafts. High-altitude aircrafts can fly at altitudes greater than 30,000 feet above sea level. This class of airplane is usually powered by jet engines and is used for specialized tasks such as atmospheric studies, research to simulate satellite platforms, and other applications where a high-altitude platform is required. High-altitude aircrafts are good for acquiring large aerial coverage with typically lower spatial resolutions. So they're useful for reconnaissance and are used for collecting more systematic data for large areas. And then photogrammetry is the discipline that developed that includes the creation and application of techniques that allow one to measure areas on the ground from actual photographs. Individual photographs that come from an airplane don't come georeferenced. They don't have lat and longs and are often taken on an angle. By using techniques within photogrammetry, aerial photography developed so that you can accurately depict geography and make maps of these different photos. They can act as the base to take surveys of large areas. These are aerial photographs that have been stitched together using photogrammetry techniques. Here are two examples using aerial photography. Most of the high quality data you see on Google Maps, like when you're planning out your trip, you go to Google Maps and you zoom into the city and actually see like really specific areas of that city. You're actually seeing stitched together aerial photographs that have been georeferenced via these photogrammetry techniques. Likewise, photogrammetry made it possible to assess elevation over large areas. Previously, they were kind of surveys that had to take place over vast distances on the ground, which takes a lot of time. But by comparing multiple different photographs and conducting these measurements using photogrammetry, we are able to create these USGS topomaps, which you see here on the right, which cover the entire US with accurate elevation data. So the remote sensing platforms satellites, this slide here is showing space shuttle remote sensing. Much later than aircraft-based remote sensing data came satellite remote sensing. This is space shuttle-based remote sensing, which has some of the advantages of aircraft remote sensing and some advantages of satellites, but also some of the drawbacks of each. At right is a model of a space shuttle collecting elevation data on Earth, and that's one of the really useful reasons to collect data via a space shuttle, is that you can get multiple measurements, multiple images of the same location, and use these methods of photogrammetry to calculate what the elevation is within all areas of that photograph. So here on the left, is a really common advanced use of space shuttle remote sensing. It's called synthetic aperture radar interferometry. I know it's a long word. Don't worry so much about that, but I just want to emphasize that this is a technique that allows millimeter scale measurements of deformation of landscapes, so you can see really small changes in the elevation of a location. In this example, the center of the above image, where there are bands of several colors radiating outward, shows swelling in this area around a volcano in Oregon. And then, of course, there is satellite remote sensing. There have been hundreds of satellites launched around the world, all with different capabilities. They are good for scientific applications when you want high quality data over moderate spatial scales, and you want that data systematically collected over time. And there's tons of different types of satellites. Remote sensing platform satellite geosynchronous, which is a type of orbit, and it means it's fixed in one location. So it can take images continuously of that same location. This is useful for large-scale changes in the atmosphere, for weather, forest fires. It keeps imaging the exact same spot. On the right are some examples of this type of orbit, this type of imaging. Superstorm Sandy, you see here on the top right, that's before it got to New York. Bottom right is from August 2020 when fires in Northern California just started out. And although it's not super high quality data, you can track and see where the fires are and where they're developing over time, over a couple of days, and see that change. And then we have the polar orbit. This means they are swinging around Earth at different rates, which means they are crossing over at the poles as they are orbiting the Earth, and this allows them, as they are doing that orbit, to take closer in pictures as they go pole to pole and back down pole to pole on the other side of the Earth. They are able to get higher quality images over time, but do so a little less frequently than geosynchronous orbits. These satellites constantly orbiting around Earth allows us to get quality images over time. This is the fires on the photo on the right here in 2020, which was taken on the Terra satellite, which is able to get a daily image of California because it revolves around the Earth so frequently, allowed daily tracking of the fires. Another example of a remote sensing platform based on a satellite is the Landsat satellite. It's higher quality than we saw with the image of the California fires, but you have a trade-off because it takes longer for the Landsat to travel back to that same location. So you don't get like daily tracking, it comes at a less frequent rate. This is the Palm Springs area on the right, so it's actually two different images of the same area in Palm Springs, and you could see, comparing the image on the left versus the right, the amount of urban sprawl. It's a huge development of urban area over time from the left to the right image. Sun synchronous satellites orbits are the most common orbits used for Earth observation remote sensing. Sun synchronous satellites are typically 400 to 600 miles from Earth, orbiting around the globe from pole to pole and collecting information for the entire planet. This reoccurring collection of information enables analysts to track change over time and potentially make predictions about the future. It is important to note that these satellites are not geostationary or fixed to collect information from a single location. Imagery collected with satellite platforms such as Landsat is often open source and easily accessible. Satellites are an ideal platform for global monitoring and environmental science applications. Unmanned aerial systems, otherwise known as drones, are increasingly more popular as a remote sensing platform. The term UAS includes other components that make up the system, even like the pilot is included in this. I will usually say UAS or drone from here on forward. All sorts of application areas have been developed for drones in the last 10 to 20 years specifically. This allows us to gather data for a phenomenon. It's more than just taking pretty photos or using a drone for concerts and live images or a live event. What we're going to do in this class is look at the different ways you can actually collect durable data that's useful for many different applications and then how we can analyze those. This image here on the left is an aerial image from a drone of an ag field. Just, it's all green as you would expect from a nice, healthy ag field, right? But then showing visible parts of the electromagnetic spectrum, it all looks pretty green to me But the image on the right shows the infrared part of the spectrum and allows us to see indications of plant health that read much better than what the human eye can see. This allows farmers to apply insecticides to areas that aren't doing so well. So it's really useful. Remote sensing platforms, unmanned aerial systems, can also include unmanned aerial vehicles, UAV, and drones, like I mentioned. But there's also drone surveying. This is useful for urban planning and construction applications, site planning, upkeep of infrastructure, like the power lines on the left that you see here, 3D maps of buildings in the middle picture on this slide. And then you can also update property boundaries in cities. You can get actual visuals, including these orthomosaics, which are similar to the aerial photography images that we talked about before. You can make 3D maps like these buildings that kind of pop out and are really cool for urban planning purposes. Or you can come up with like an actual 3D model via LiDAR, which again, we'll talk more about that later on in this class, but those are the main platforms as considered in geospatial applications. And in geography, an important takeaway from these first few slides is that all these methods are useful and sometimes not useful. They all have advantages and disadvantages for whatever reason you are using remote sensing data. There's a number of factors to consider. First, you want to consider the quality of data, and then areas of data collection. So just because something is newer or flashier, it doesn't mean it's necessarily the right tool all the time. Some of these trade-offs listed on this slide here introduce some more technical terms for some of these attributes that I'll talk about later. But clearly a drone can get more detailed information about that area than a satellite. But an airplane or a satellite can certainly beat a drone in terms of how much data is collected in one day. So revisit intervals, that's some satellites like geostationary or geosynchronous can take continuous pictures of Earth in a given spot, whereas a drone mission may require substantial setup and involvement and cost, and each time you wanted to record data, that would go up. Then there's the length of data records. Some satellites have been flying around for 10, 20 systems. Systems of satellites have been around 40 years. They might not have the highest quality, but you can look at those changes over those 40 years, which is pretty important and may help solve some, the problem at hand. And then, of course, there's cost. This is often a limiting factor, especially for student projects. If you have these, grand ideas of what you would love to do with a bunch of high quality drone data, that actual cost is quite significant and it adds up over time. And then if you're doing a construction project with a pretty big budget, you would probably be willing to pay that cost for some really high quality drone data. But for a lot of research or class projects or environmental applications, the free government produced satellite data, which we'll get into this next week or two, works just fine. Here on this slide, I've listed some limitations of remote sensing. At the top includes seasonal changes. So remote sensing data can be affected by seasonal changes such as vegetation growth, snow cover, or changes in weather patterns, which can affect the accuracy of the data. The impact of seasonal changes can limit the usefulness of remote sensing data in some applications. Another limitation is human-made structures. So remote sensing can be affected by buildings, roads, bridges, which obscure the underlying natural features and make it challenging to interpret the data accurately. The impact of human-made structures can limit the accuracy and usefulness of remote sensing data in some applications. And then another limitation is electromagnetic interference. Remote sensing can be affected by radio waves, power lines, other sources of electromagnetic radiation, which can affect the quality and also the accuracy of the data. The electromagnetic interference can limit the reliability and usefulness of remote sensing in some applications. And then remote sensing data can be complex and challenging to process, requiring specialized tools and softwares, which can limit its accessibility, to non-experts. The limitations of the data processing can limit the usefulness and accessibility of remote sensing data in some applications. And these are just to state a few. So I've talked about why we use remote sensing, what remote sensing is, limitations, some main elements of remote sensing like the platform and the sensor. But now I'm going to discuss the overall process of remote sensing. So like a pretty brief overview of the process. Here in this diagram on this slide, it'll help to illustrate this process. So when electromagnetic radiation passes through the atmosphere, and interacts with atmospheric particles. So that's number one, going to number two. And during this process, as a result, there are different mechanisms of interaction, and that includes absorption, scattering, or transmitting energy through the atmosphere, which we'll talk about later in detail. And then the transmitted energy will be able to reach the surface of the Earth and form interactions with Earth features. And so that's from number 2 to number 3. Another form of interaction will be created here, number 3 here. And then there are 3 forms of interaction that are created. It's reflection, transmission, and absorption. Reflected energy will be reflected and censored by the satellite sensor, number 4. Passive remote sensing, we follow this path. And so I'll get into active and passive remote sensing later, but this process includes passive remote sensing as well. And so passive remote sensing, we follow this path. So the reflected signal from the Earth's signal is going to be censored from the satellite sensor to be recorded, to be a recorded measure. And then this recorded measure will then be sent to the ground station to be processed. So that's number 5. And after looking at this graphic, we can conclude remote sensing is inferring surface parameters like vegetation height or canopy from measurements of the EMR from Earth's surface. So why remote sensing? Data can be obtained through remote sensing. You can collect information for a very wide area. Second reason, it gives a good documentation of change. I talked about the different orbits of the satellites, and that helps to support different amounts of and frequencies of change over time. So you could see a great detail of change over a long time. Land use, land covered, assessing areas for agriculture or urban landscape, to name a few. And the Landsat satellite imagery started in 1972. So we also have all those satellite images ranging back from 1972. The third reason for remote sensing is I like to quote the famous quote here, seeing is believing. So the human eye is only capable of seeing 0.4 to 0.7 micrometer wavelengths, and that is a very small portion of the electromagnetic spectrum. So if we only just relied on human eye, we would be limited to 0.4 to 0.7 of the electromagnetic spectrum. But we also have infrared, X-rays, ultrasound, so many wavelength ranges with which we could explore with remote sensing. So that's why remote sensing is really important. And then number 4, it helps you extract information and also analyze it, which we will get into later this semester. So I've talked about what remote sensing is, why it's important, some limitations, the elements, the overview and the process of remote sensing. And this next lecture, next week, we will get into the electromagnetic spectrum, and we'll talk about energy interaction, energy interactions in the atmosphere specifically, and then with the Earth's surface, and we'll also talk about vegetation mapping. Thanks for watching our first lecture, and please make sure to always watch the lectures first before attempting any labs or the activities posted under the corresponding week. And do not hesitate to reach out with questions. Thank you.